Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, we're happy to welcome both Kostas and Jason who give us two game theory talks today. Please.
Hi, I'm glad to be back. So today I'm going to talk about some interaction of what I call probabilistic approximation theorems to solve certain game theory and optimization problems. And so the talk is pretty modular. So it has 4 modules, and you can stop me at any time. So I'm not sure how much I'll cover in 45 minutes. So so physicists tell us that there is uncertainty that's inherent in the physical world, but as this picture may convince you, there's also uncertainty in the social environment. Okay, so this is an interesting T-shirt. So that's rock paper scissors, right? So so what I'm interested in this talk is to see to look at uncertainty in optimization problems, game theoretic problems, auction problems, and I'm going to look at stochastic uncertainty, right? So Bayesian uncertainty is useful in these settings. So in the game theoretic setting, it's the randomization that enables Nash's theorem. In the auction setting, it's randomization that enables Meyerson's theorem. Okay, so the design of revenue optimal auctions is enabled by modeling the uncertainty in this environment in a Bayesian way. And in the optimizations, generically, modeling uncertainty in a stochastic way allows us to go from worst case to average case analysis. Okay, and get stronger results. On the other hand, this comes with difficulties. So in these settings, uncertainty makes a problem hard to solve. So the hardness is in the form of PPD completeness. Over here, we don't know how to generalize this important result to multidimensional settings. And generically, Bayesian uncertainty introduces nonlinearity in the underlying optimization problems. So it comes with presence and it comes with difficulties. And what I want to do today is to show examples where we can somehow harness this Bayesian uncertainty to get rid of some of these difficulties. And the way we're going to do that is we're going to use tools from probability theory. Right, so what I want to do is I want to connect these two things. In particular, I'm not going to look at generically at optimization to combinatorial problems. Okay. So my first module is symmetries in games, which I've talked about before in this group. So I'm going to go through it faster. But just to, I just want to illustrate a few things with this example. So the goal of this module is to study settings, game theoretic settings, where there is a lot of symmetry. Okay. In particular, in these environments, there's no way a player is keeping track of the identities and actions of every other player in the game. Probably a player is keeping track of aggregates of what the other players are doing. And here is a model, a mathematical model to capture such settings. So I'll call a game an anonymous game if every player only cares about what he's doing and what the aggregate behavior of the other players are. So more precisely, every player suppose has the same strategy set, and then the payoff function of each player is anonymous. That is, it looks at what the player is doing, and then how many of the other players are choosing each of the available strategies in the game. As an example, congestion games can be written in this form because when I'm driving in a road network, I only care about what route I'm choosing, and then what routes the other players are choosing in a sort of aggregate way. I don't care about the identities of other players. Or if you want to be more elaborate, I can partition players into types, slow drivers, fast drivers, and so forth. But in any event, there is a lot of anonymity in the way I'm modeling the game. And examples can be drawn in other settings, social phenomena, auctions, and so on and so forth. And just a couple of references in the game theoretic literature. Starting this problem are these. So over here, a social phenomenon is started via this model, using this model. This is about congestion games. So what I'm interested in is how players reason in these settings. Okay, when there's a big population of other players, and really what affects my payoff is the aggregate behavior of these guys. All right, so what, how would Nash play this game? Okay, no, that's a joke referring to the afternoon session. Okay, so how would Nash play this game? So here's some results I want to talk about. So in joint work with Christos Papadimitriou, we solve these games. In the following notion of solve, we compute for any given precision in polynomial time an epsilon approximate Nash equilibrium of these games. Okay, and to do that, we have to understand how players reason about what they have to do given the aggregate behavior of the other players. And these results are enabled by approximation theorems that sort of approximate the aggregate behavior of the other guys. And I'm going to show examples of what I mean by that. But in reality, it all reduces to theorems about sums of indicator random variables or multidimensional versions of indicators. Okay. So let's be more precise. So in an anonymous game, the Nash equilibrium is some vector of, say, there are 2 actions per player. Every player is just choosing a probability. So the Nash equilibrium lies in this space. Okay, so every player is choosing a probability, and there are n players. All right, so the Nash equilibrium is somewhere here. So I have to search the space that's high dimensional. These are independent indicators because in Nash equilibrium players are independent. And really, if I look at this as an optimization problem, what is the objective function? Or more generally, if this is the real Nash equilibrium, and instead of that, I look at this point, how well does this perform? How well of a Nash equilibrium is some other point that's sort of far from the actual equilibrium in this space? So what's the right notion of distance, if you want, in this space that I'm interested in? So it turns out that the relevant distance function is the total variation distance between the sum of these indicators and the sum of those indicators. In other words, if this is the real Nash equilibrium and this is epsilon close to the Nash equilibrium under this distance, then that's an epsilon approximate Nash equilibrium. Okay, so that will take this as given. It's pretty straightforward. But what I want to do to find an epsilon Nash equilibrium is to come epsilon close to the actual Nash equilibrium, where the distance is measured by the total variation distance between the sums of the 2 indicators. The sums of these indicators versus the sum of those indicators. And generically, the way I want to solve this problem is to cover this space with epsilon balls in this distance. So I want an epsilon cover under this type of distance.
I'm missing something in the notation.
Yeah.
The xi, are they numbers in 0, 1, or are they indicator variables?
They're indicator variables.
So you wrote there
It's
0, 1, 2,
right. It's isomorphic to this space. So the space of all mixed strategy profiles is isomorphic to the hypercube. But so I'm looking at this space, the space of all vectors of indicators. And what I showed in the previous slide is that if I have a mixed strategy profile, so a vector of indicators, and a different mixed strategy profile, how close are they in the
where are the indicators?
You're asking about this? Why it's isomorphic to that? So, for this example, suppose every player has two strategies. So a mixed strategy is just an indicator for each player, right?
Okay.
So
it's an indicator in the case when you have
two strategies, and more generally is this, it's what I said here, it's a categorical random variable. Okay, so some point in the sequence. Right, so right, so that, my point was that if this is a Nash equilibrium and I come epsilon close to the Nash under this distance, then this is an epsilon Nash equilibrium. Right? And the idea, the generic way to find the Nash equilibrium would be to cover this space with epsilon balls under this notion of distance, right? And then I'm guaranteed that one of these points is going to be epsilon close to the Nash equilibrium. So I'm going to exhaustively go over each of these representatives, one representative per ball in my cover, and check if that's an epsilon Nash equilibrium. Okay? And obviously the problem is that this is high dimensional, and potentially the number of balls could be huge. And what we showed with Christos is that there is a polynomial number of balls that covers this space, which was sort of like we didn't expect originally. But just to relate it to the types of approximation theorems I want to construct, here's an example approximation theorem that we need to come up with to design such a cover. So here's the theorem. So for any collection of indicator random variables with arbitrary expectations pi, these are independent, right? And any given constant delta that does not need to depend on n or anything else, it's an absolute constant, there is a way to construct another collection of indicators, yi, with expectation qi, so that the expectations of these guys are restricted to be multiples of delta. So these are, of some finite precision, if you want. And at the same time, the total variation distance between the original given sum of indicators and the constructed sum of indicators is a function of delta. So you don't get the penalty of n that one would expect from this restriction. Okay, so generically, if you are restricted to use multiples of delta, you will expect an n coming into this bound. What we show is that there's no n coming into that bound, and that enables polynomial size covers. Okay, so in particular,
in terms of the best function possible of delta.
So the best I can do is delta log 1 over delta. I don't know if that's optimal. It's optimal. It's almost optimal for n equals 1. But potentially, if you have more, you can use it. I don't know. Okay. If you have a bigger number of indicators, you might be able to use it somehow. All right. So, but in any event, this enables constructing covers of this size, and then you can exhaustively go over them and find a Nash equilibrium. Okay. So, and then it boils down to, if you want a faster algorithm, you need a better cover. Okay, and the best we can do I'm not going to go over this other theorem, but the best we can do right now is something of this form. So I can cover this space under this notion of distance with some polynomial number of balls in n, the number of indicators, and some function of epsilon that's quasi-polynomial in 1 over epsilon. All right? So, and I can convert then looking for an epsilon Nash equilibrium to searching over a space of this size. And as an open problem, whose answer I don't know, I don't have strong belief of whether a better cover exists or not. Okay, so as an open problem, is there a cover of the space that has size polynomial in both n and 1 over epsilon? Okay, that's an interesting question. Okay. Yeah.
The dimension there?
Is it easy to see how to go? Excuse me?
How do you get from exponential many, say, balls that you need to cover polynomial? So the existence of this yi.
Right. So you're asking, how do you go from the theorem to bringing down the number of balls? How do you use the theorem to?
How do you prove the theorem?
Right. How do you prove the theorem? Yeah.
I mean, if it's like a couple of lines.
So it's not exactly, but it's not exactly 2 lines. But you use so. Okay, so one important ingredient is that this function is symmetric over the indicators. So to begin with, there is already some reduction you can do. That's not going to give you a polynomial reduction, but the problem is symmetric in permutations. And then using that and using the theorem I presented, you can bring down the dimension. Okay, so. Because this is symmetric and because I can restrict each of these guys to choose from a finite set, there is only so many, there's only polynomially many possible permutation variants, classes of collections I can make. Yeah? All right, so. That was my first application. Right. So, and what I want to talk about now is a different setting, in an auction setting. I want to talk about what is called multidimensional pricing. I'm going to explain what that means, but some history first. So that problem falls under the more general class of problems called optimal mechanism design. Where basically the goal is to come up with an auction that optimizes the revenue of the auctioneer. And such auctions are known for certain settings. And maybe the most celebrated result in this realm is Meyerson's auction, which basically does the following. So it's a revenue optimal auction under the assumption that the bidders are quote-unquote single parameter Bayesian. I'm gonna say what that is. Okay. So I'm gonna clarify what single parameter Bayesian means and what closed form means in the statement of the theorem. So by single parameter Bayesian, I mean that it's a strong assumption. Basically, what it says is that every bidder who's participating in the auction has the same value for each of the available items. All right. So if the auctioneer is selling many paintings, then every bidder has the same value for all the paintings. Okay. That value is random, but it's a single value for every painting. Okay. No matter if it's Picasso, Mondrian, my value is the same. Okay. And that value is a random number.
It's independent picks from the same distribution, or one pick and then all of them?
So every bidder has a distribution, and his value for every painting is a single draw from that distribution. right? But different bidders may have different distribution. It's a pretty restricted setting if the items are heterogeneous, right?
For the same bidder, different items, the values from the different picks from the same.
No. One pick. One pick. So that's a restriction of the theorem. What is good about this theorem is that it's not generically searching overall. It's not a theorem saying that there exists an optimum, right? It's a theorem that says that the optimum has a very precise, elegant form. In particular, it says that the auction that optimizes revenue is really the auction that optimizes, the virtual welfare of people. Okay, I'm not going to get into the details of that, but it's a very precise characterization of what the optimal auction is doing in this setting. All right. So that's what Myerson says, and following Myerson, one of the most important problems in this area is the generalization of this theorem to the more natural setting of heterogeneous items where an agent has different values for the different paintings in the auction. So the multi-dimensional setting. All right, so we want to have a same kind of theorem for the multi-dimensional case. So there is a large body of work in economics looking at this problem. And recently also computer science has been interested in that. So, just to mention a couple of recent papers on this problem, basically, as far as constant factor approximations to the optimal revenue go, the problem is solved. Okay, so we know we have very good, very elegant auctions that achieve a constant factor of the best revenue. All right, so in terms of constant factor approximations, the problem is solved. What I want to talk about here is if we are interested in not getting a constant factor approximation, but almost all the revenue that we can possibly get. Okay, so I'm presenting here joint work with my student Yang Kai on a closed form, efficiently computable one-minus epsilon optimal revenue mechanism for if in the case there is a single bidder. Okay, so I'm looking at this problem, but for a single bidder. All right, and I'm going to talk about some different work for generalizing that to many bidders. Okay, so maybe this all seems abstract, so let me just make it more specific. So basically, the pricing problem is the following. Okay, so there is one customer, and I have the gallery. Okay, I have a gallery with many paintings, and there is one customer. I've posted prices on my paintings, right? And the customer comes in and wants to decide what painting to buy, right? So how is he going to make that decision? He's going to basically say, oh, this painting is worth V1 to me. This other painting is worth V2 to me, and this one is Vn, right? And I'm going to pick the painting that optimizes the difference between my value and the price it has. And I'm going to pay the seller the price of that painting, okay? The price of the argmax of the gap between my value and the price.
So players with limited capital might opt to maximize the ratio and the difference.
That's right, okay. Right. Okay. That's right. Okay, and the ratio is not such a big problem because I can take logs, but in principle there could be an arbitrary function, okay? So economists usually look at that. Okay, so I can handle logs, I can handle ratios, but I'm not sure if I can handle more complicated stuff. So the point is that, so I have the gallery, and I want to decide on the prices to optimize this objective. And in principle, if I have no idea about the values of the bidder, of the buyer for my paintings, I cannot solve this problem, right? But what do you have Bayesian information about the values of the buyer for the paintings? So this is the setting I want to look at. Right? So I know that, and I'm going to assume that the values are independent random variables. So I have a distribution for the value of this guy for each of the paintings, and these are independent rows. If they're not independent rows, there's not much I can do. Okay, so the problem is highly inapproximable if there are correlations. So now, what is the optimization problem I need to solve? Well, I can write, there is a closed form expression for what I need to optimize. So let me walk you through it. Okay. So
one generalization between the general case and the event case, just assume there's one in the scaling factor that's common to all the.
That's yeah. That's usually that can be handled in some cases by Myerson. Okay, that's right. But let me walk you through the expected revenue. Okay, so if I have posted prices P1 through Pn for my paintings, and the values are random variables, then really my revenue is the buyer is going to pay price Pj with probability that the gap for the jth item dominates the gaps for all the other items. That's what this guy says. And really what I want to do is I want to optimize this objective function. So I want to find the prices to optimize this function, which has a closed form expression, right? It's not computed by an oracle or anything, right? So it has a closed form expression, but it's highly nonlinear. So the these guys are drawn from this distribution. So
all this is subject to the gap being positive.
that's right. Yeah. So you're right. So right. So I want to add another positivity constraint there. Okay. Thanks. Right. So I'm looking at the unity bound case. We can talk about some additive buyer case or other settings. So I'm going to restrict my discussion to the unit demand guy, the unit demand setting. So this guy wants to buy one painting for his living room. And this is the way he's going to decide about it. And this is the expected revenue that I'll get. Okay. So what do we know about this optimization problem? Well, we do have results. So again, in terms of constant factor approximations, the problem is solved. So there is a paper by Jason, Suchi, and Bobby giving a polytime constant factor approximation for this problem. So the result I wanted to talk about with Yang Kai is that we can get approximately arbitrarily close to the optimal solution, to the optimal revenue, under the assumption that these guys, the distributions, are more than hazard rate distributions. All right? Or if each of them is supported in a balanced set. Okay? It's not spanning, because in some sense, the input complexity of the problem is, it would be principal exponential. The support of these distributions could be exponential in the description complexity of the distributions. Right. So I wanna avoid this case. Okay. Right. And notice that like even the IID case or other restrictions is not easy to solve. Okay. Even I don't know the support 3 case. If every distribution has support 3, it's not easy to solve. Okay. So. Right, so how do I about solving that? So this is again restating my optimization problem. The way, in general, the way one goes about solving such a problem is to establish some smoothness properties of the objective function. So what I would like to do is, for instance, to argue that if I change this distribution by epsilon in total variation distance, that's not going to kill it's not going to, destroy my revenue. Okay? Or if I restrict my prices to a discrete set, this is not going to kill my revenue. Or, if I restricted prices further to be supported where the value distributions are supported, which is a natural thing to do, that the objective function is not, I don't lose a lot of revenue. So the problem with this problem is that it's highly non-smooth, okay? So all of these, you can construct examples where, each of these, first attempts is going to fail, okay? So it's hard to, establish any smoothness properties on these guys or these guys, all right? So what we do, so the way we go about this problem is this, right? So, so suppose this is a circuit that is hardwired the value distributions of the buyer for the paintings, and for every selection of prices, outputs the revenue distribution, okay, of the seller. So it's a distribution because these are deterministic, but these are distributions. So for any choice of prices, this circuit, right, is going to sample these distributions and output some revenue. So there is a revenue distribution coming out of the circuit. And what I just said in the previous slide is that the usual way one goes about approximating such a problem is to establish smoothness properties for this side and that side, and massage that to get a polynomial cover of the space of all possible choices on this side. Okay. So instead, what we're gonna do is to look at this guy directly. So look at all possible revenue distributions that can arise by selecting prices for my problem, and try to argue that I can reduce the dimension of that space. So this is a scale. This is a scalar random variable. That's the important thing. Okay. So I want to cover. What we do with Young is we try to cover a space of scalar random variables rather than covering an n-dimensional space of prices. Okay? So again, in the same framework as before, suppose that this is the space of all possible revenue distributions that can arise by choosing price vectors. Okay? So each price vector is going to induce a different revenue distribution in this space. And again, the question is, what is the natural notion of distance between a collection of prices and another collection of prices? Because I'm going to be covering this space under this appropriate notion of distance. So it turns out that if you look at this problem this way, the distance function that is relevant is some sort of dual of the total variation distance of these guys, which is the smallest distance such that I can perfectly couple these guys, these two random variables, so that they're never apart by more than delta. It turns out that this is the right, this is a good notion of distance you can play with. And what the result is that again, there is a small cover of this space. And this time, it's an implicit cover. So we cannot provide a closed form description of this cover. But we can argue that there is an algorithm which, given the FIs, is going to generate this cover. Okay? So this is what we do. And we optimize, find the best price vector. So this if you have this in place, you can get almost near optimal revenue, but this does not go through unless you use two more ideas that are the structural parts of our approach, the structural parts of the theorem, and here's some interesting things we can show about this problem. So the first theorem I want to show is labeled by a constant number of price suffices to get 1 minus epsilon fraction of the revenue. So what I mean by that, and then the other one is a single price suffices for IID. So the first theorem says that for any desired epsilon, a constant number of prices or of different price levels suffice if you're shooting for 1 minus epsilon fraction of the revenue. So basically what this theorem says is that the epsilon you want to achieve dictates how many prices, how many different price levels you're going to choose to achieve that revenue. So this function is independent of anything that has to do with the problem.
So G does not depend on these, but the prices themselves will depend on.
That's right. Right? So this theorem says that no matter what your problem is, the instance is, you're guaranteed that if you're shooting for a 1 minus epsilon fraction of the revenue, you will only ever going to use G of 1 over epsilon distinct price levels to achieve that. Right? So that's a strong theorem that says that nothing to do with the instance, the number of different price levels you're going to use. G, no, it's more like 1 over epsilon log 1 over epsilon. It's almost linear. So the other structural theorem we established is that in the case of IID, in the case that the FIs are IID, so this theorem says that if there is enough items, a single price suffices for getting 1 minus epsilon fraction of the revenue. And the number of items you need to get that depends on the epsilon you're shooting for. Okay? So if you're shooting for a bad approximation, okay, then a few items suffice. Right? If you're shooting for something better, this function again doesn't depend on anything that has to do with the instance. It just tells you that if you have many identical items, a single price will suffice to give you the revenue. Okay, so these are structural theorems we show. So, looking at the problem on the revenue side, plus these two structural theorems imply the theorem I showed before. Okay, so generalizing Meyerson for the case of monotone hazard rate distributions. Okay. So,
The last one was kind of surprising intuitively that even if it's IID, but even the distributions have very large range, there's no advantage to have different pricing.
Yeah, so intuitively what this says is that if you look at the extreme value distribution, this works for, for monotone hazard rate. So the extreme value distribution for monotone hazard rate distributions behaves nicely. So there is a point that's going to give you most of the revenue.
I make a comment here, actually. It's for IID distributions. So you're pricing paintings, and the guys have the same distribution for each painting. Actually, it wasn't clear that you should use different prices. Right? Why should you post different prices on these paintings when they have the same distribution?
No, you might want to hedge, right? You may want to give a low price to be on the safe side and a different price to hit the tail, right? So that's what you want to say, right? And it turns out that for monotone hazard rate, the tail behaves nicely. So the extreme value distribution, the maximum value, drops sufficiently fast so that you can hit it.
And you have a damper so that you need the multiple.
I don't expect that this would be true for, say, regular distribution. Okay. Multidimensional mechanism design, so trying to generalize the previous results to auctions rather than a single bidder, to many bidders rather than a single bidder. And that's joint work with my other student, Matt Weinberg. So recall, a broad question is generalizing Meyerson's result for the multidimensional setting, where I have different values for different items. Recall also that this problem is solved as far as constant factor approximations go. And here again, with math, what we show is that randomness, again, looking, using this Bayesian viewpoint, we can get 1 minus epsilon fraction of the optimal revenue for certain scenarios. So I'm going to give you what we have. So that's fairly recent, so it's not even written up. Eh?
Is it written down?
What?
Is it written down?
Okay, so what we have is efficient randomized mechanism to get 1 minus epsilon fraction of the optimal revenue in the following scenario. Okay, in 2 scenarios. Okay, so the first one is this. So the number of items is constant, but the number of bidders the bidders can be many. The bidders are IID, so the valuation functions of the bidders are IID, so bidders are identical. Okay, their valuation functions come from the same distribution independently. Now, what is the valuation function of each bidder? Okay, so it can be one of 2 kinds. So either, so we're looking at the valuation function of a particular bidder. Either his values for the items are independent from MHR distributions, or they can be arbitrarily correlated, the values of a bidder for the items. Except again, I need the balance condition. So every distribution is supported on an interval whose ratio is bounded. And in general, if it's not bounded, I get a result of this kind. Okay, so I have to pay the log of the ratio in the exponent of the running time. All right, so that's the case of a constant number of bidders, a constant number of items, identical bidders, IID bidders, and then the valuation functions of the bidder can be either arbitrarily correlated with this balancedness condition, or they're independent, not necessarily identical from MHR distributions. So that's the first result we have. And the other one is the flip side of that. So a constant number of bidders and many items. 2 minutes. Yeah. The case in this case, I assume that basically everything is IID. Okay. So the value of every player, every bidder for every item is IID from either a monohazard rate or a balanced distribution. And again, I can generalize it in this way. But just to conclude, where does the randomness come into play? All right. So, to get this result, we're going to use randomness to do some kind of dimension reduction in our problem. And for those of you who have read Nash's original paper, what I'm going to say is going to ring a bell. Okay, so Nash's paper, his paper where he showed the existence of Nash equilibria, he established another interesting result, that randomization can also buy you some symmetry, some structural symmetry in the solution concept, in the Nash equilibrium. So for example, if all the players are identical, there is a Nash equilibrium where everybody's using the same mixed strategy. More generally, if the utility functions have any type of symmetry, there is a Nash equilibrium that respects that symmetry. In fact, there is always a Nash equilibrium that respects any kind of symmetry that the game has. This is a fairly general result. So we show the same thing in this setting. So suppose that D is the distribution of the bidders' values for the items. So there are n bidders and m items, so that distribution is supported in this set. So now let S be a set of permutations on the bidders and on the items so that this distribution satisfies this symmetry. So if I permute the output of the distribution using permutation sigma from that set, the distribution remains the same. All right, so let S be all the symmetries that the value distribution satisfies. So what we show is that there exists an optimal randomized mechanism that respects these symmetries. So what that means is that if the mechanism is given as input a permutation of a vector of values of all the bidders for the items, then the output of the behavior of the mechanism is the same as running the mechanism on the unpermuted vector of values and then permuting the results. Okay? And that's only true for randomized mechanisms. It's not true for deterministic. Deterministic mechanisms are not going to have these symmetries. Randomized mechanisms do, and this is what randomness is buying. Okay? And as I said, recall Nash's symmetry theorem. All right. So I'm pretty much done. I had a last application, which I'm going to skip. Coming to conclusions. So problems in economics involve uncertainty. Right. That either comes in randomized strategies or beliefs. Which one?
Just the last.
Okay.
Part of your talk.
Okay. Mechanisms. Yeah.
So for item pricing, you post different prices. You got a bidder who's IID,
right.
One bidder who's IID,
Right.
and you post different prices on the different items.
That's right.
What would be the symmetric version of this that you're talking about? Are you posting lottery prices? Is that what you're doing, or
You could do you can give a single lottery for every you can post symmetric lotteries.
so you're going from item pricing to lottery pricing when you're adding randomization?
Yeah.
Got it.
So right, to conclude, problems in economics involve uncertainty, which is usually modeled in Bayesian way. That introduces complexity in the form of PPAG for computing Nash equilibria, but it also enables result. Nash's theorem, the symmetries in Nash's paper, Myerson's result, and so on and so forth. And we need probabilistic techniques to understand this Bayesian uncertainty and use it constructively in applications. And today I talked about anonymous games, auctions. I didn't talk about that. Thanks a lot.
All right, I want to thank Kostas for preceding me and solving a problem that I had thought about for several years. So thanks, Kostas. Good. We're going to switch gears, still talking about mechanism design, but we're going to talk about some topics related to crowdsourcing. And I want to start with a sort of motivating scenario. So I'm a theoretician academic. I give talks and stuff, and occasionally I get emails from people saying, send me your title, your abstract, your bio. OK, all good to go. But very rarely, but occasionally, a talk-related graphic I have to send in to these people about my talk. And where am I going to get a talk-related graphic? I don't know. Like, I can't draw. So fortunately, there's the internet. And fortunately, there's this website, TaskCN, which is unfortunately in Chinese, but fortunately it exists. And this is a crowdsourcing website. And this crowdsourcing website specializes in the design of graphic images. Right? So if you have a graphic image that you need made, and you know someone who speaks Chinese, then you can use this website to get your image made. And so here's how it works. Basically, you post a description of the task you want and a reward. So I said design a graphic depicting crowdsourcing, because it was this was for this talk that I needed the graphic. And the reward, the best design wins $120. OK, then the hard part is you wait a week. And then you have a bunch of submissions, and you pick the one you like the best, and you pay the guy 120 bucks. OK, so
do you have to pick one?
there are various semantics. I think, so I did pick one when I did this for getting a graphic for describing this talk with the help of a visiting student, actually a Shouty Dang student visiting me for the semester. And so you're probably dying to know like what submissions I got when I said, draw me a picture.
Are the rules requiring you to pick one?
I believe so. I believe there are ways to weasel out somehow if you can say none of them meet some minimal requirements, right? Because you can post requirements, and if you can say none of them meet the requirements, then you don't have to pick one because none of them met the requirements. Good, so I received a bunch of submissions. So some of them looked like flowcharts, which I didn't really like too much. I guess this flowchart's a little bit better than the other flowchart. Then you get some kind of artistic pictures which don't really make much sense to me, and some horrible, horrible pictures which neither make much sense nor have much artistic quality. And then some reasonable diagrams that like, okay, there are a lot of people contributing ideas, and there's one idea that really worked. Okay, this is getting better. More flowcharts, but more graphically oriented. Okay, so what was the best one that we got? So the best one that I got was this picture, which has, I guess, someone posting a task to the crowdsourcing tree with multicolored apples, and a bunch of people who are completing tasks and getting money. Good. That's what we're doing. So that enabled me to make this really attractive-looking banner that was posted all over Northwestern for my talk, which otherwise I wouldn't have been able to do. So good. So crowdsourcing is a great thing. So I'm going to now speak about the theory of crowdsourcing, and my main motivation in coming at this was the following observation. I just made a lot of people draw pictures, and I basically threw all the pictures out except for one of them I liked and posted that picture all over Northwestern. And so, what's that? I got 18. I didn't show you some of the worst ones. So I wasted a lot of work, and this, of course, made me nervous because I'm into optimization, and I just did something that wasted a bunch of work. And I kind of was curious as to, so there are two questions, right? Can I show that I didn't waste too much work? And the other question is, well, what if I just gone and hired someone like the traditional way and said, you're an expert in drawing stuff. I'll pay you your hourly rate, $120, how much time that is. So you work for 2 minutes, and then you draw me a picture, right? And do I get something better or worse? I mean, how does that compare to crowdsourcing? Okay, so I want to answer these two questions. So my talk is in two parts. The first talk, I'm going to review some auction theory, which I'm then going to use to describe the theory of crowdsourcing. And the auction theory is going to be actually pretty quick. And then we're going to talk about crowdsourcing. Okay, so that's the agenda. Good. So here's a single item auction problem. One item for sale, n bidders with unknown private values for the items. And each bidder wants to maximize their utility, which is the value they get for receiving the item if they receive it, minus the price they pay. And I want to design an auction to solicit bids and choose the winner in payments. I could have, if I was doing auction theory, have two possible objectives, probably either to maximize the social surplus, meaning I want to give the item to the person who values it the most, or I could be trying to maximize the seller profit, meaning the total payments I get. Okay, so let's see what happens in maybe the first auction we might think of. The first auction you might think of maybe is the first price auction. So solicit sealed bids. The winner is the bidder who bids the most, and charge the bidder their bid. Okay, so as an example, if I got these bids, then the person who bid 6 wins, and they pay me 6. Good. Another auction you might have thought about when I said, well, what's an auction? You might have thought about the second price auction, which almost the same thing, solicit sealed bids. The winner is the highest bidder, but then we charge the winner the second highest bid. Okay, another auction rule. So again here, the winner is the person who bid 6, but now they pay me 4, the second highest bid. Okay, good. So as an auction theorist, here are the kinds of questions I want to be able to answer about these auctions. So I want to know what should happen in equilibrium in these auctions. And I want to know if we're playing in equilibrium, then what is the outcome? Can I predict the outcome of the auction? Okay? And once I've done these two things, then I can start comparing auctions. If I wanted to maximize social surplus, if I wanted to maximize profit, I could say, well, which auction has higher social surplus in equilibrium, or which auction has higher profit in equilibrium. Then I can sort of optimize this once I've solved for what the equilibrium is. Okay? So let's talk about doing this equilibrium analysis. And the first thing that you might do is say, let's take the second price auction and let's look at Vigory's work, which shows that bidding your value in the second price auction is a dominant strategy. Okay, and so you can assume that bidders bid their value, and so that when you select as a winner the bidder with the highest bid, that's also the bidder with the highest value, because it's a dominant strategy to bid your value, and so you've given the item to the agent with the highest value, so you've maximized social surplus. Good. So that's the equilibrium analysis for the second price auction. That was easy. Okay. Let's now do the more challenging case, the first price auction. Okay, so we're doing this auction. I want to know how should you bid in this auction. Okay, of course, this auction does not have a dominant strategy, meaning you never want to bid of course you don't want to bid your value in this auction because you always get charged your bid. And if you bid your value and you get charged your bid, then if you win, you get 0 utility, right? Because your bid is equal to your value. So you never want to do that. And in fact, if you knew the second highest bid, you'd always want to bid epsilon above that if your value was above the second highest bid. But you don't. Okay, so there isn't a dominant strategy. Okay, so I want to have a little quick review of probability so that I can talk about what's going on. I'm going to use all of my examples with a uniform distribution so things are nice and easy. Okay, so if I draw a random variable v, and I'll do random variables in red in this talk, from the uniform distribution on the interval 0, 1, then what do I have? Well, a cumulative distribution function, which I'll call capital F, is the probability this random variable v is less than z, and that's just z. Right? And the density function is, of course, the derivative of the distribution function, which is 1. Okay? The expectation of v is just the integral of the value times the density function, which is 1 here, so it's 1/2, which is this picture. And I'll do most of my proofs by picture. So what is the expectation of g of v? Well, it's the integral of g of v, which is, if I had the picture, it's the green area minus the red area. So that would be positive in this picture because the green area is bigger than the red area. Good. Okay? And the last thing about expectations, uniform random variables that I'm going to use is uniform random variables evenly divide the interval in expectation. So if I had 2 uniform random variables and I sorted so v1 was bigger than v2, then the expected value of v1 is 2/3, and the expected value of v2 is 1/3. Right? Good. So that's my review of that. Now, back to first price auctions. So you and I are bidding in a first price auction. Let's assume that our values are drawn from the uniform distribution. Okay? So I want to figure out how you should bid. Okay? And I'm going to tell you how I'm bidding. Let's suppose I bid half of my value. Okay? And now you know that my value is uniform 0, 1, and I just told you I'm bidding half my value. So you know I'm bidding uniform 0, 1/2. Right? And so now, given your value, you can solve for what you should be bidding. Right? So let's just do that really quick. So your utility is a function of your value and your bid. Right? And if you win, then what's your utility? It's your value minus your bid. Right? Because you win, you get your value, and you pay your bid. So if you win, it's your value minus your bid. So what's your utility for bidding b when your value is v? It's your value minus bid. Neither of these are random, times the probability you win, which is random because it depends on what I do. Okay, so what's the probability you win? Well, that's really easy. That's the probability that your bid is bigger than my bid. What's my bid? My bid is half my value. Okay, so let's rearrange. So that's the probability that twice your bid is at least my value. My value is uniform 0, 1. So this is just the CDF of 2b, which is 2b. Okay? So I get a formula which is v minus b times 2b, good, which is this. How do I maximize that? How do you maximize that if you want to figure out your optimal bid? Well, you take the derivative set equal to 0 and solve it, and you get you should bid v over 2. So I just showed you what you should do given what I was doing. But notice, so what's the conclusion? You bid half your value. But I was bidding half my value. So if I bid half my value, then you want to bid half your value. But if I know you're bidding half your value, then I also want to bid half my value. So that's an equilibrium. Okay, so that's a Bayes-Nash equilibrium. That's what we're going to talk about in this talk. Bidding half your value is a Bayes-Nash equilibrium. What can we conclude from this equilibrium analysis? Well, who wins? If everyone in the auction bids half their value, who wins? The person with the highest value wins. So again, it maximizes social surplus in equilibrium, just like the second price auction did. Okay, good. I now want to talk about, is that the only equilibrium? Yes. I'm not going to prove that in this talk, although I could, if you gave me another 30 minutes. If you all gave me another 30 minutes. Okay, good. So now I want to talk about profit. We talked about social surplus. First price and second price are the same. I want to now quickly talk about profit. What's the profit of the second price auction? Again, two bidders, uniform values. Well, that's easy, right? Draw values from the unit interval. V1 is less than V2. What is my profit? Well, it's the expected value of V2, because I get as payment, the highest bidder pays the second highest value. So what's the expected value of V2 here? It's 1/3 by the assumption they're uniform. Okay? What about the first price auction? What? False. Half? 1/4? 1/3. Thank you. It's 1/3, right? Because your expected profit is equal to the expected highest bid. What's the highest bid? Well, the highest bidder bids half of their value, right? So the highest bid is 2/3, right? But he bids half his value, which is 1/3 in expectation. Okay? So they actually have the exact same expected profit too. They have the same surplus. They have the same profit. This is not a coincidence. In fact, it's one of the most important theorems in auction theory, which is two auctions with the same equilibrium outcome have the exact same expected revenue. And in fact, the theorem is more precise than just this. It actually happens once I know my value in the auction, I have the same expected payment. Okay? So in the first and second price auctions, if my value is V, then my expected payment in the auction is the exact same. And so I'm just going to use this notation, payment of V, to denote the payment that I have in the first or second price auction if my value is V, in expectation, because they're the same. Okay? Good. I now want to turn to another auction. I want to talk about the all-pay auction. So an all-pay auction is the following. I again want to sell a single item. I have a bunch of bidders, so I solicit sealed bids. The winner is the person who bids the most. Everyone pays their bid. Okay? So as my example, bidder 6 wins. Everyone pays. Clear? Good. I want to now solve for the equilibrium in this game. And then the way I'm going to do that is I'm first going to guess. I'm first going to guess that probably the bidder with the highest value is going to win in equilibrium if the bidders are IID, right? Because they should be bidding the most. If the person with the highest value wins, well, then the equilibrium is the exact same as the equilibrium in the second price auction, and I can use the second price auction to figure out what my payment should have been. Okay? So what should the equilibrium strategy be to get this equilibrium where the highest valued agent wins? Well, in the all-pay auction, our bid is equal to our payment, right? Now, so my bid as a function of my value is equal to my payment. But remember, payment is just a formula. It's the same for all pay. This is the expected payment. This is the formula. This is the same for the all pay, the first price, the second price auction, right? So what is that formula? Well, that formula is, it's just the second price auction payment. Okay, so let's break that down. What do you pay in the second price auction? Well, you only pay if you win. So if you win, you pay the second highest value given that you won. Okay, so let's do an example. 2 bidders, uniform 0, 1. If your value is V, what do you expect to pay in the second price auction? Well, the second highest value, given that you win, well, that's the expected value of a uniform random variable conditioned on being less than your value. So that's half your value. Okay, so this first term is V over 2. And the probability you win, given your value is V, well, that's the probability he's below you, which is just the CDF, which is V. Okay, so V squared over 2, that's what you should bid in a 2-player all-pay auction. Okay? And of course, if you do that, that verifies my guess that the highest bidder wins, right? If you do that, then the highest bidder will win. Good, so my guess was right. Yes?
So this assumes that the values are uniformly distributed, all this analysis?
This last example assumed that, but everything else assumes their IID. Okay? Good. Okay, so that's my overview of auction theory. I now want to relate auction theory to crowdsourcing. So here's sort of a first attempt at modeling crowdsourcing. I post a reward that I normalize to $1. And then contestant I comes, and they have some skill, which is how good they are at producing images. And they make some effort. They work. And their effort times their skill is the quality of the picture they make. Okay, so the quality they make is, which I'll call P, is just their effort times their skill. Good. And this agent receives some reward xi for doing the work, which I'll say is either 0 or 1, whether it's 0 if he doesn't get the reward, or it's 1 if he gets the reward. Okay? And so what's his utility? His utility is the reward he gets minus the effort he puts in. Okay? Good. And what's our goal in crowdsourcing? Well, I want to maximize the best quality submission that I get. Okay, so I want to optimize the maximum payment. Okay, I want to compare this setting to all pay auctions. Okay, so what happens in an all pay auction? I have one item to sell, and I have a bidder I who has a value VI for receiving the object. They bid and pay the same amount, so I've just used the same variable for their bid and their payment, which is just PI. Good. I again choose the outcome, who wins, xi 0 or 1. And what's his utility? Well, his utility is his value times the probability he wins, or times whether he wins or not, minus his payment. Okay? That's your utility in the all-pay auction. And your goal usually, maybe in the all-pay auction, is to maximize your revenue, which is the sum of the payments. Okay, so I want to compare these two things because the utilities look kind of different. And I want to note that from this bidder's perspective, his value is a constant. So I can multiply this equation on both sides by his value and say he's just trying to optimize this thing. Right? If he optimizes his value times his utility, that's the same as optimizing his utility. Right? And now the objectives are the same. Okay, because VI times EI is just PI by definition.
The player in the crowdsourcing, what variables does he control? Just whether xi is 0 or 1?
He controls EI. That's his effort. Okay, so basically the utilities are the exact same thing. And so what do we know? We know if the utilities are the same, then what happens? Well, the equilibriums are exactly the same. Okay, so that analysis we just did solving for equilibrium, we're done. We know what goes on in crowdsourcing auctions. Okay, the difference between, so they have the same equilibrium, but the difference between crowdsourcing contests and all-pay contests is here our revenue is the sum of the payments, and here the payments of the losers are wasted. Okay, that's the big difference, and that's the focus of my talk, is understanding what's wasted, how much, and good. So crowdsourcing contest, everyone works if losers is wasted. It's like an all-pay auction. Otherwise, I want to compare crowdsourcing contests to conventional procurement, right? What if I just hired the best guy, or what if I was the government and I did some auction where people sort of put in proposals and then I picked the best proposal and only they did the work, right? So this proposal system is kind of more like a second price auction or a first price auction, right? And so if you're trying to get good revenue in the second price auction, you would just get the full set of payments, right? And we know from revenue equivalence that all pay and first and second price get the same total revenue, right? So my only question is how much work is wasted, right? Because that wasted work is work I could have gotten in the second price auction doing regular procurement.
So you're measuring the wasted work by the PI or the EI?
By the PI.
So a more skillful worker, you value his wasted effort?
Yes, yes. I value wasted work by the PI, and I note that had I run a second price auction or a first price auction to do this procurement, I could have gotten the full sum of the PIs as payment because only the first guy pays, only the highest guy pays, right, in the revenue equivalent. So there's no wasted work, and it is the payments I'm talking about. Okay?
I have no exposure to the VI or the EI, only to their product, right?
Yes, you only know PI.
So when you purchase this picture, are you entitled to have all the most too, or just?
No, I cheated by showing them to you. But pretend you didn't see them, okay? Because otherwise, I mean, so usually, and the assumption I'm going in here is that you're trying to get crowdsourced something that you can't combine, right? If you got a bunch of payments, if they were money, you could just take the sum of the payments, right? But I'm imagining these images, there's no way to combine the images I got to get one image that I wanted to post on my flyer.
But you just combine them.
Yes, for the illustration of the talk, we kind of went around the model. But let's ignore that. Good, so this is what I was just saying. So basically, I just want to quantify this loss of wasted work, and it turns out it's not that hard to do. So this is the main theorem that I wanted to tell you. The main theorem is that the highest payment is at least half of the total revenue that you would have gotten if you collected all the payments. Or in other words, the highest payment is at least the sum of all the losers' payments. Okay? Good, so that's what I want to show. I'm going to give you the proof of this on this one slide. It's pretty concise. So I'll have two variables, W and L. W is the expected winner's payment. L is the expected loser's payment. And I just want to show that W is bigger than L. Okay, so what is the winner's payment? Well, remember, payment of V is this sort of, we know if your value is V, we know what you bid, right? You bid your payment. Okay, so your payment is payment of V times the probability you win if your value is V. That's the winner's payments. And the loser's payments are payment of V times the probability you lose if your value is V, which is 1 minus the probability you win. Good, so what is W minus L? Well, it's your payment of V times 2 times the probability you win minus 1, right? Just regrouping. Okay, so let's go back to previously in the talk where we solved for what payment was. And remember, that was the expected second highest value conditioned on V winning times the probability of V winning. Okay, and so to avoid myself writing V winning all the time, this probability, I'm going to remember that for the uniform distribution, that's easy. Probability V wins is just V to the n minus 1, right? Because it's the probability you're above each of the n minus 1 other guys, and you beat each one with probability V, and so the probability you beat all of them is V to the n minus 1. Okay? So this seems not very general, like it's only for uniform distributions, but you can get the same decomposition just by changing variables into probability space instead of value space. Okay, so the same proof is general, but let's just do it for uniform so we don't get confused. Good, and I'm just going to call this thing, so I don't have to write it out again, G of V. Okay, so here's my new equation. I get, this is again my payment, G of V times V to the n minus 1 times this 2 times probability of winning, which is this. Okay? So I want to calculate the expected value of this. G of V is complicated, but this term is easy. So let's do the easy thing first, which is calculate the expected value of this term without the g of v and see what we get. Okay? So I claim that this is at least 0. And you can work this out for any n. But here's a picture which shows you that that's at least 0. Right? The green area is bigger than the red area, so it's at least 0. Good. But furthermore, look at this picture. There's more positive area to this side than that side, right? And if we know one thing about g of v, we know it's monotone increasing, right? So it's got bigger values towards this side. Okay? So I'm taking, what is this expectation? It's the weighted sum of g of v with this thing that's increasing weight on this side. Good. So g of v was a monotone function, so I've got more weight here, so the whole thing is positive. All right, that's it. So, some conclusions. We modeled crowdsourcing contests as all-pay auctions. We showed the loss from wasted work is small. A major workhorse of this theorem was the revenue equivalence theorem, which made it all easy. Okay. There are two other results in the paper that I'm referring to here, which I didn't have time to talk about. And one is solving for optimal crowdsourcing contests. And so let me just say quickly what one of the questions you could answer is. So we gave all the prize to the best participant. Well, I don't have to do that, right? So for instance, Topcoder is a crowdsourcing website for programming. And they give 2/3 of the prize to the best guy and 1/3 to the second best guy. Is that a good idea? Is that optimal for some distribution of values, or is it not? Right? Remember, we still only get the value of the best contribution, but somehow we reward the second guy for his effort. Thanks for playing, we'll give you 1/3 the prize. Right? Is that a good idea? So the answer is no. Among static allocation rules, meaning if you fix in advance that you allocate to the highest guy, or some static rule like you allocate some fraction to the highest, some other fraction to the second highest, some other fraction to the third highest, and you fix that in advance. Amongst all fixed in advance rules, which rule do you want? You want to always go with the highest guy. Okay, so Topcoder is doing something stupid. And another question you could ask is, well, maybe after seeing the qualities, I can adjust the amount I pay. Right? And then if you try to do this, this takes a form a lot closer to what Kostas was referring to as maximizing virtual values. And so you can derive virtual values for the maximum payment and then optimize virtual value, and that optimizes the maximum payment. And you get similar results there, except that, unlike in the auction case, these virtual values depend on the number of players. So the more players you get, you do different things. Okay? And the last thing that we did, which is I don't really know how to sell this because I don't know the economics literature that well, but I'm told by economists that they didn't know that for n-bidder IID distributions that the first price auctions and all-pay auctions had unique equilibrium. And we prove that. And we prove it basically using revenue equivalence. Whereas the proofs in the literature, in the economic literature I've seen for analyzing first price auctions and all-pay auctions use differential equations, which is why they do it for n equals 2. And so they know the equilibrium results for n equals 2, but for general n they don't know because the differential equations with n functions are complicated. Right? And so we do it with revenue equivalence for n players in IID settings. And I'm assuming they don't know it because people I've talked to were like, whoa, really? But it is also really easy, so I'm surprised. All right, that's that.